MAT video, but this is a really short video explaining why this sequence makes sense. Now, most people will think, hey, that's paradoxical. Infinity positive numbers cannot equal a negative number. Well, I'll show you that this can be calculated from the infinite series formula. A over 1 minus R. So the A's first term, 1 over 1 minus 2 equals 1 over minus 1 equals minus 1. Our geometric series formula says this is so. It's interesting, right? When you think about it, this can be expressed in binary notation as this. Sounds a bit paradoxical, don't you think? But all computer scientists will see, something looks familiar here. Well, what is it? So let's say we're only dealing with an 8-bit structure. We have 8 switches here. Now, if we turn the last one on, obviously all 0, and then the last one on is 1. But when we turn the first one on, it will be a negative number. This is called 2's complement representation. Now you make all of them on equals to negative 1. That makes sense. Now you can continue this with 16-bit, 32-bit, 64-bit structures. But essentially, binary is just an infinity-bit computer. You get it? You get the analogy here? So if binary is just an infinity-bit computer, then our number we're representing as negative 1 is 1, 1, 1, 1, 1, 1, 1, 1, an infinite number of ones here. You know what? And another reason why this makes sense is because when you add 1, there's no other place to the left. And so 0, this gives you 0 equals to 0. Hey, that makes sense. Now you know why this sequence makes a lot more sense than you first thought. When you think from another perspective, everything starts to make sense. That's the thing about maths. Well, anyway, see you in another MAT video. Hurrah! And now our magical white box cleaner has cleaned this up for us. Okay, you still remember last sequence? 1 over 1 is negative 1. And what we can do is that we can subtract 1 from both sides to get negative 2. Since this is in binary, we are writing it this way. Then we have 1, 1, 1, 0, 1, then 1, 1, 1, 0, 0. Wow! Infinity-bit negative representations without having to do a negative sign. Isn't that brilliant? Well, it's just an alternative number representation in terms of binary. Well, we can continue the same way using decimal. So we have 9999, then 99998, 99997, and so on. Well, it's just alternative number representations, and one alternative number representation that is often used by computers is, can't remember, is it single precision or double precision? Anyway, it takes up 32 bits. It's times 1 bit, the exponent's 8 bits, and what's called the mantissa is actually 23 bits. So basically, so you have A, B, C, so it's negative 1 to the power of A. So A is 0, it's positive, and A is 1, it's negative. Then B is the exponent, 2 to the power of B minus, you guessed it, 128. It's called the bias. And then you have to multiply it by what's called 1 point C, where C is the binary representation and the 1 point is the start of the mantissa. Well, I hope you got it. Well, we get the gist of IEEE double precision notation. And I have often dreamed of a notation. Okay, you got this? Yeah? So you have 0.000, so it's 8. Let's say this is 8 because we're so arbitrary. This is a similar floating microfloat representation, it's called. And then you have 0.111, then we until 15, and 00, then 01.00016. Now here comes the revolutionary bit, 01.001. What? Now it's 18, 01.01020. Wow, that's really cool. Until we get to 11.111, which is 120. Interesting notations, right? Well, let me tell you, it is darn interesting once you look at it from a different angle. So basically, this is like our exponent, and this is like our mantissa. You get it? Well, if you don't, then try building up your own number representations. And anyway, thanks for this. Thanks for spending my time talking about residues and reverse notations and this microfloat representations, and goodbye.